Okay, so let's talk about the next part of the front end, known as parsing. So if you remember, I showed you this picture last time, and I said the front end has to do a few different steps. And the first one is translating the high-level language to data structures. The first part of that is scanning, figuring out the keywords, white space identifiers, punctuation, etc. And when we scan, we use regular expressions to identify all the tokens in the language. Once we find all those tokens, we want to make sure that the tokens are happening in a meaningful sequence. And we achieve that through the process of parsing. And this is where we derive the syntactic structure of the program and verify that it's a legal program, at least with regard to the grammar. Okay, so if lexical analysis identifies the vocabulary of the program, the words and punctuation, parsing figures out if the words are in a valid structure. For example, what if you have the sequence of tokens identifier, assign, number, semicolon for the C language? Is that a meaningful and valid structure? Well, hopefully you recognize that as a legal sequence of tokens in C, right? You can assign some identifier to a number, having something like x equals 3 semicolon, right? So that's legal. Well, we want a formal way of representing this structure. And the way we do that is with a grammar. A grammar gives a precise syntactic specification of a language. The great news about it is that it can automatically be converted into a parser in much the same way we were able to generate a lexer from a set of regular expressions. And this makes it easy to construct tools for translation of input programs and error detection. So here's an example of what a grammar looks like. And this is a grammar for very simple arithmetic expressions. And what we have here are two rules. One rule is called the expression rule, and the other rule is the op rule. And the op rule says that an op can be either a plus or a minus sign. And the expression rule says that an expression can be a number. This bar means or, so it can be a number or an expression followed by an operator followed by another expression, right? And here, where we have operator, we could, this expands to this rule below, which is either plus or minus. So this could be expression plus expression or expression minus expression. Or an open paren followed by an expression followed by a closed paren, or it's a minus sign followed by an expression. And everywhere you see expression in this grammar, you could resubstitute in another representation for an expression, in full generality. So I could have the expression inside parentheses could be another expression that's inside parentheses. So this grammar is really very expressive in terms of all the different expressions that it can represent. Okay, now usually when we talk about programming language grammars, we're talking about a class of grammars known as context-free grammars. And a context-free, the word context-free tells you something really important about these grammars. It means that the meaning of the language is completely independent of, or I should say, the meaning of any part of the language is independent of some outside interpretation, right? Some program, if it's written, two programs written the same way always mean the exact same thing, in the context of the language you're considering. It's context-free, right? Whereas English is not context-free, right? The sentences I'm saying right now sometimes only make sense because of who I am, right, and who you are, right? Y'all know a lot about electrical and computer engineering, and so when I talk to you about this information, it makes sense to you. We're on the same page. But if I were to describe this to someone else, they might hear me saying completely different things. So context matters a lot in spoken language. But in a programming language, we want to eliminate context as much as possible, so the language only has a single, well-defined meaning. Now, the attributes of a context-free grammar, and this is just taken from the theory of languages. And we're not, I'm not going to justify any of these things. We're not going to look into this more deeply. I'm just going to tell you what they are, and we're going to use these concepts. So a context-free grammar has a set of tokens known as terminal symbols. These are the tokens that come from the scanner. So these are the tokens defined for a very specific language. So they're a set of tokens. Then there are a set of non-terminals. And these non-terminals are the things you can put tokens together to create, like a statement in the C programming language. Right? Then you have a set of productions, and these productions tell you how a non-terminal can be made up of terminals or tokens or other non-terminals. And then we always have a starting point. We have a non-terminal in the grammar that says, how you know when parsing is complete. It's called the start symbol, which is a little bit contradictory, but it's the unit that we're trying to parse. And usually the top of a grammar is something like program. You want to match a whole program, and so then you define everything a program can consist of. Okay, so we already looked at this grammar for expression, so let's go back and look at these pieces that I said have to be there for a context-free grammar. First, parsing has to begin somewhere. Well, generally when I show you a set of rules, parsing begins with the first rule. So what we're trying to figure out is if some sequence of characters is an expression. And so expression is the first rule. This is where parsing starts. And op is just a rule that's going to support that. Then we have a bunch of tokens, or otherwise known as terminals. And these are things that come directly from the lexer, right? When the scanner or the lexer is analyzing a set of input characters, it's going to identify some as a number, it's going to identify some as a plus or a minus, or an open paren or a closed paren, or a minus sign. These things are tokens. They're going to come straight in and be directly usable by the parser for whatever they are. On the other hand, non-terminals are not something identified for the lexer. They're something specified by the grammar. Right? If I have a number, then a number is an expression. Right? Or if I have a plus or minus, then those things possibly are an op. So non-terminals are things that are created from tokens or from other non-terminals. Right? And then the productions I was telling you about before are the rules that describe how to make non-terminals. So in this case, expression is made up of 4 rules. An expression can either be a number, it can be an expression op expression, it can be an expression in parentheses, or it can be the negation of an expression. Right? These are the 4 rules. There's no other way to make an expression other than these 4 rules in the grammar. Okay, so when we're going to parse some input string, we need a grammar, and then we need to know if that input string can in fact be recognized by the grammar. If it can be recognized by the grammar, then it's said to parse. So one way we figure this out is by drawing a parse tree. Parse trees are a pictorial representation of how a parser works. So let's walk through this. Let's say I have an expression that looks like this. Minus, open parentheses, 1 plus 2, close parentheses. Let's figure out if this expression is, or if this program can in fact be parsed by the grammar that we've been looking at. Okay, so the first thing we should do just for ourselves is kind of tokenize the input, because we don't care if the numbers are 1 and 2 or 199 or 5,361 and something else, right? They're numbers. So when we tokenize it, we can just look at it like this. Minus open paren number plus number close paren. Those are the tokens. And we want to know if these tokens fall into a pattern that this grammar can understand. Okay, so the first thing we can do is apply rule number 1. And rule number 1 says that a number is an expression. Right, and when I'm saying rule number 1, I'm referring to these numbers that I've put here on the grammar. Normally when you specify a grammar, you wouldn't have numbers like this. I've only done this to make the slide easier to understand. So if I ask you to write a grammar at some point, don't put these numbers, unless you're explaining to me, right, how the grammar works. So rule number 1 says a number can be converted to an expression. So what I'm doing here is in my drawing, I'm going to show number connecting to expression. And now that means in some ways that means I'm replacing number with a new rule that says a number is really just an expression. Likewise, I can apply rule 5, which says a plus sign is really an op. So I'll connect plus to this op symbol as I draw the parse tree. Okay, the next thing I can recognize is that expression op expression here in rule 2 can also be converted to an expression. So I can replace expression op expression with a single expression. Okay, the next rule I can match is rule 3, where I identify that a parenthesis followed by an expression followed by a parenthesis is also an expression, right? So these 3 symbols, this open paren, the expression I just created, and the close paren come together to make an expression. And now lastly, I can apply rule 4. And rule 4 says that an expression is also minus followed by an expression. And now I know that there's a minus sign here, and that what comes after it is all one big expression. And so minus followed by an expression is an expression. Okay, the parse tree, therefore, proves that there is a way to understand, this program I started with in terms of this grammar for expressions. So this program does parse with respect to this grammar. So if you can draw a parse tree for a program, then it will parse on the grammar that you're using. In other words, it's a valid program for the grammar. Okay, it's important to differentiate this from being a valid program for the language, right? Because it could be the grammar for your language doesn't represent all the rules that are possible for that language. And so the grammar is one step of validating the program, but not all of the steps. But at a minimum, if you can draw a parse tree, you can say that the program is valid for the grammar. Okay, it may or may not be valid for the language. Now, on the other hand, if you can't draw a parse tree, then it doesn't parse. And because it doesn't parse, you know for sure it's an illegal program for both the grammar and for the language. Okay, now here's another example. Here's I have an expression here, 1 minus 3 plus 4. And according to the grammar, there are 2 possible ways for this expression to parse. In one way, I subtract 3 from 1 first, right, represented by this expression here. And then after I subtract 3 from 1, then I'll add it to 4. However, there's another interpretation. And in the other interpretation, I would first add 3 and 4 together. And after I've added them together, I would subtract it from 1. Now, which one of these is correct? Well, if you say the one on the left side is correct, then you're probably basing that on your knowledge of algebra and our basic conventions for how operators work. And your intuition about that would be correct. However, the reality is that the grammar is ambiguous and allows both. There is nothing in the grammar I showed you that says that one of these is preferable to the other. Okay, the reality is the left one is the one we want, but the grammar is ambiguous and it allows both of them. So this is a problem. This means we have an ambiguous grammar. And just the most general definition for an ambiguous grammar is one that allows multiple parse trees for a given input. In general, we want to avoid grammars that are ambiguous. If you think about it, this means that there's a program that has two different meanings. And I don't know about you guys, but when I write a program, I don't want it to have two meanings. I want it to have one meaning. So when it comes to programming, we really want a language that has exactly, we want a language to have a grammar that is very well specified, and for any given program can only have one meaning, one parse tree. So we need at least to add something to our grammar on the previous slide that says, when you're considering two alternatives, you should pick the one that groups things to the left, right? So we need some sort of rule in our grammar like that. And in fact, if you think back to C, and when if you took 209 from me, or if you took 209 here at NC State, then we talked a lot about operator precedence. And in fact, that's kind of the problem we're dealing with here. What we really want to have happen is that we want operators to the left to have higher precedence than operators to the right. And so in our grammar, we need to specify precedence rules. And that is in fact how you handle this problem. You would specify precedence. When you have an option of either performing the operator on the left first or the operator on the right first, then you can tell the grammar that there is a desired precedence. And then during parsing, we can enforce that the one on the left happens first. Now another way to do it is that you rewrite the grammar and you add more rules to make it explicit which one should happen first. And both of these approaches are reasonable and are used. Okay, so the next thing we're going to talk about in the next video is how we can actually go from an idea for a grammar to a program that implements that grammar. And there is a lot of theory out there behind this process. If you feel like I'm skipping over a lot of details, you're absolutely right. There are people who spent years and years and years studying this problem and perfecting it. And for the most part, the research in how languages work and how they are parsed is well understood. It's so well understood that if you write out a grammar, there are tools that will automatically convert it into a C program that will parse that grammar for you. Right, so there are parser generators the same way that there are scanner generators, and we're going to look at some of these parser generators. However, you shouldn't let this fool you into thinking that this is an easy process. It's not. A lot of research went into it for a long time. It's just that's not the topic of this course. From what I understand, there is a course in the CS department that deals with the front end, that deals how parsing works in great detail. So if parsing is something that fascinates you and you want to learn more about it, computer science offers a course about that. But we're not going to get into exactly the way parsers work in a lot more detail. Instead, we just want to understand these basic concepts of what a grammar is and how you can know if a program can be parsed by a given grammar. All right, thanks guys.